Hello, this is the solution to College Physics, Chapter 3, number 29. So, King Arthur's knights fire a cannonball from the top of a castle wall. The cannonball is fired at a speed of 50 meters per second at an angle of 30 degrees. A cannonball that was accidentally dropped hits the moat below at 1.5 seconds. How far from the castle wall does the fired cannonball hit the ground? Alright, so there's a couple of things that are important here. So first off, it's telling us that it was launched at an initial velocity of 50 meters per second, but that is a vector that's going a little bit in x and a little bit in y. And that split is determined by that 30 degrees. How much is going to go in the x direction versus how much is going to go in the y direction. A cannonball that was accidentally dropped hits the moat. That one tells us how much time it would take if the ball were just simply rolled off the side and let to drop from the height of the wall. And that's going to come up important in a second. And we want to know basically what this distance right here is between the wall, the base of the wall, and the position where the cannonball lands. So the first thing we want to figure out is how high is the wall. And we can use this red arrow and the time given for the ball that was accidentally dropped or let to roll down to figure out how high that is. Once we know how high that is, we can go on to the next step, which I call step B, if you look over to the right. So step A is figuring out that height. Step B is figuring out the maximum height. We're going to call that H top, the top height. And then once we have that information, we're going to know how high it went overall by adding those together. And we can just use the last segment, C, to figure out how long it would take if it were basically dropped from this height to hit the ground. With that total amount of time, we can figure out using the initial velocity component that was in the x direction that's going to be here, to figure out how far outward or away from the wall it can get at that velocity for that amount of time. So let's get started. So like I said, step A is to use that information about the dropped ball to figure out how tall the building is, the castle wall. So I'm going to call this the height of the wall, h sub w, and I'm going to set that equal to the acceleration of gravity, 1/2 the acceleration of gravity times t squared, plus the initial in the up-down direction y times the amount of time that it fell. So we think about it for a second. This ball was dropped. It wasn't thrown. So that means that this term here is going to drop to 0. That simplifies our equation a little bit. Now we can just plug in the numbers. We know g is negative 9.81 meters per second squared. Again, if you haven't done it yet, make sure that you include that sign convention just to be safe. And then we're solving for height, and we know the time is 1.5 seconds. We do our math, and that should come out to about 11 meters. So the cannonball that was launched are 11 meters off the ground. Then the next step, now that we know how high it is, we're going to come back to that number later. We need to know the distance from the wall to the highest point. So basically, how high is this segment here, B? To find that, we have a couple of things we need to think about. First thing, we know that the velocity at the top is going to be equal to 0, right? That's why we actually chose that segment. And that's going to make our math a little bit easier if we take this piece by piece. And so these strategies you're going to learn along the way, they just take practice. And we decided to take this piecemeal. So we figured this part out first. Now we're figuring out how high it's going to go. And then once we have that information, we'll know the total height, and we'll deal with the last step as it comes down. All right, so that means that if we have the v at the top, which is like the final velocity, and we set it equal to the initial velocity in the y direction for the cannonball being launched, plus 2a delta y, this term is going to drop out to 0. And it simplifies our equation. Make sure you include the squares. I just realized that. We're going to get an equation that looks something like this. So you have v naught y hold on, let me see. I'm going to get an equation that looks like this. Delta y, equals negative v naught y squared divided by 2 times a. In this case, the initial velocity isn't going to be the full 50, and we have to think about what portion is going to be going upward and what portion is going to be going sideways. So first, we know that that segment is going to equal 50 meters per second, the magnitude of the hypotenuse, times sine of that 30 degrees. And that's going to get us that portion. So we'll just plug that in. We got negative 50 meters per second times sine of 30 degrees. And all of that's going to be squared. On the bottom we have 2, and then we have the acceleration of gravity, which is negative 9.81 meters per second squared. And when you do all of the math, remembering that this is negative, that's going to help us out. It should come out to 31.9 meters. So the height on top of being 11 meters off the ground is going to add another 31.9 meters to the height. Now the big question is, how long is it going to take for it to go up there? And then we're going to figure out how long it takes to go all the way down, not just the 31.9 meters it went up above the wall, but also plus the 11 meters as it comes down. First things first. So the next step will be to figure out how long it took for it to get up to the top of the arc and then back down. So to do that, we're going to move on to the next slide. And we're going to use a couple of kinematics equations. The first one being the final position or final velocity when it gets to the top, which is going to be 0. And that's going to equal the velocity it had originally when it left the cannon in the vertical component only, plus the acceleration of gravity times the amount of time it's up in the air. Right? Remember, we're looking for time here. So we're going to rearrange this, solve for time. So we end up with t equals negative velocity, the y component of velocity, over gravity. And plug those numbers in. We're going to get something looks like this. So we got the negative, and we're only going to take that one component of the 50 meters per second. And this time, again, we're going to use the sine 30. And that's all divided by negative 9.81 meters per second squared. Right? If you're not sure how we got the sine 30, just remember you have your triangle. This is the 50 is the magnitude, and the degrees were 30. And we're looking for the y component right here. So in this case, we'd have velocity naught of the y component. All right, so that's where we got the sine 30. Do our math, and it comes out to 2.5 seconds. So it took basically 2.5 seconds for it to get up to this point after it left the wall. Now we want to figure out how long it's in the air for this part right here. So to find that out, we use somewhat the same idea, but we have to think a little bit, because now it's not just falling back the 31.9, but it's also traveling 11 meters on top of that, the distance that it was off the ground when it was launched. So in order to get that, we know that the total vertical distance traveled on the fall is going to be the 31.9 meters that it went up from the cannon, plus the 11 meters off the ground that it already was, and that's going to get us 43 meters total falling distance. From there, we can use that distance total and the rest of the kinematic equation. We know that gravity is acting on it for however long it's in the air. And we know that the initial velocity, and this is where we're going to be tricky, we're going to start from the top, and that's why we broke it up. Right? So starting from this point, looking at this last fall as its own problem in itself, allows us to drop that term and simplifies our equation a bit. And we are solving again for t, so we need to solve and rearrange the equation for t. That gives us something that looks like this. All under a radical. We plug in our numbers, we end up with 2 times negative 43 meters. Remember, it's negative because it's falling that distance, so displacement is a vector, and so it has the direction. It's important, and that's going to help us out here when we do the math, because we know that the acceleration of gravity is negative. That needs to cancel out under the radical, otherwise we'll end up with some imaginary numbers, and we know that the total time for it to fall from the top here to the bottom here is 3 seconds. So all told, it's going to take 2.5 seconds on its way up, and it's going to take 3 seconds on its way down. So the total time in the air is going to be equal to the sum of those two, which is 5.5 seconds. All right, so the next step now is to use this number, but now use all of the numbers to calculate the horizontal distance. Remember, our ultimate goal was to calculate this distance right here. So, set up our equation. We're looking for the distance it travels in the x direction. Going to stick to this kinematic equations helping us out. And we need to make sure we remember the initial velocity we're talking about here is going to be that component of, it's going to be this component of the cannon launch, right? So it's just this component, and that's going to equal the total magnitude times cosine of 30. And that's what we're going to be plugging into this equation right here. Do remember that this term's going to fall out. There's no deceleration or acceleration because we're assuming that drag is negligible. And that leaves us with a simplified equation. Delta x equals v naught of x times t. And we are solving for v naught because we want to know how fast. No, actually, we're solving for delta x. So now we can just plug in the numbers for delta x. We know that it was traveling at 50 meters per second times cosine 30. So just this component right here. And we know that it was doing that for the 5.5 seconds before it hit the ground. We do our math, and that should come out to 240 meters. And that's our final answer. So if we go back, do a little sanity check, we realize that this part here is the 240 meters we were looking for. And that concludes the solution to problem number 29.